Okay, welcome to the next part of the video series on additional maths. So this section, add maths, and again I'll put plus P2 because it's almost all relevant to the P2 course as well. And this section is about exponential and logarithmic functions. So I'll write the full word here. Exponential and logarithmic functions, but a lot of the time I'm just going to write exp and log log. Keep it simple. So what topics are we going to cover here? Alright, first of all, basic properties. Basic properties of exp and log functions. In particular, I'll talk about the graphs and other function type stuff like domain, range, and the relationship between the two types, exponential and logarithmic. And a few other important properties. Now, after we've covered those, we're going to go on to the laws of logarithms. These are basic rules about addition, multiplication, division, which I think a lot of students will know already. So anyway, you can take a look and see if you already know it. Then I'm going to talk about special bases. So you may or may not know a logarithm has a base. Those special bases are really just two, 10 and e. And if you don't know what this number e is, let me just write its approximate value. Okay. If you don't know about that number, I'm going to give you some ideas about it. So the next section will be about the number e, about what it means, why it's special. It's not very obvious. Now I have to say that little section there about the number e will not be examined anywhere. It won't be on the exam. So you can skip it if you're not interested. Couple more things after that. Equations and inequalities. Really, how do we use this knowledge that we develop up here to solve problems, to find the answers to equations and inequalities using obviously exponential and logarithmic functions. And the last section is going to be about what we might call the linear law problems. That's not a very good name, to be honest, but it's good enough. And that will be important because that kind of question is very common on the exam. Alright, hopefully, let me just review before I start the main section. Hopefully you're going to find this is quite a short area of study. It won't be too difficult for most students. But I do want to emphasize that although the basic properties that I've mentioned here, the basic properties of the function, are quite simple to understand, they are very, very important right across A-level maths, and indeed going higher, further maths and so on. So make sure you get that stuff right. Now, if you're mostly looking at this video for reviewing material for the exam, then I guess it's the stuff towards the end. Oh, and by the way, I should add a final section here. We'll look at a couple of exam questions, yeah? So obviously that will be the most important thing if you're reviewing it for the exam, but just for your general maths education, you really want to make sure that you understand the basic properties of these functions, because they are very, very important all across maths, in fact all across science as well, especially the exponential function. Alright, so in a moment we will kick off with the basic properties of these functions. Okay, sorry for that slight delay there. I'm adjusting my headset. Now, first thing we're going to do is talk about the definition of an exponential function. What is an exponential function? Probably the easiest way to understand it is by referring to something we've already talked about. We've talked about polynomials. So polynomials, we're dealing with objects like this. Perhaps we have a function fx equals x squared. So in this expression, the 2 is the exponent, or you can also call it power. And this is not an exponential function. An exponential function would be the opposite, where the variable x was the exponent. So if x is the exponent, or something with x in it, we would call it an exponential function. Okay, so x is the power. So let's treat 2 to the x as our first example of an exponential function. Let's ask ourselves, what does the graph of this function look like? If you like, you could pause the video and try and draw it yourself. Okay, so I'm now going to make my own attempt to draw this graph. I think I'll do it over here. So first of all, let me just use a little trick here. How does this work again? I'm going to turn this into a line. Excuse me, let me just pause the video a moment. Okay, so I'm now going to change that to a line. Excuse me for this. I'm a bit unused to this. So that's a line. Oh, not a very good line. So that will be our y-axis, and here, whoops, sorry. Here will be our x-axis. Hopefully, in a minute. There we go. Right. So I have my x-axis and my y-axis. I will get better at this eventually. Let me draw another line there. Okay, sorry, that's supposed to be an x-axis. Okay, now, so this is the function 2 to the x. What you could do, if you've never done this before, of course, is you could make a little table of different values of x, maybe -3, -2, -1, 0, 1, 2, 3, and then consider the correct values of f for each value of x. Now, first of all, if x is 0, then we're talking about 2 to the power 0. Well, that's 1. 2 to the power 1, well, that would be 2. 2 to the power 2 would be 4. 2 to the power 3 would be 8. Now, 2 to the power minus 1, 2 to the power minus 1, that's obviously 1 over 2. Well, that's 1 over 2. 2 to the power minus 2, that's 1 over 4. And 2 to the power minus 3, that would be 1 over 8. So you can easily see the pattern here is that we have a certain value 1 when x is 0, and then increasing, and I'll try and draw a curve here, but I don't promise anything. Yeah, that's not bad. And then we also have the curve continuing to go down on the other side. Oops, not a very good quality curve there, excuse me. I'll try and do that a little better. So the curve should continue to decrease. Oops, okay, you'll have to just trust me on that. The curve continues to go down as we go to more and more negative values of x. So I want you to think now about domain and range. It's a good quiz question for you. What is the domain and range of the function y equals 2 to the power x? So if we choose a domain where x can be any real number, we can see that any value of x, even sorry about that, even including 0, including positive and negative values, is allowed. We can get an answer, and the range that corresponds to this is any number greater than 0. So you notice it's impossible to get 0 for the function, because as x becomes more and more negative, f of x gets smaller and smaller and smaller, but it's always positive and it's never 0. So, admitting that my curve drawing skills leave something to be desired, this should be a smooth curve, but always positive, and always also, very important, always increasing. So if you've studied AS maths, you know what an increasing function is. It's a function whose derivative is always positive. The gradient of this function, notice, is always positive. So that's a very important point. So f of x is increasing. Its range is all positive values, or all positive numbers, and its domain can be any real number. And you should notice that this would also be true if we changed 2 to 3. If we wrote a function 3 to the x, how would all this stuff change? Well, basically, these numbers would be bigger. If I perhaps do a third column, so let's try and draw columns here. So this is fx equals 2 to the x, but if we have 3 to the x, these numbers become still 1, but then 3, 9 and 27 and so on. And these numbers become 1 over 3, so 0.3 recurring, 1 over 9, 0.1 recurring, and then 1 over 27, whatever that is, smaller. So we clearly see that the same basic pattern exists, but it's just altered slightly, and I'll try and draw this in a different colour. Again, I apologise for my curve drawing skills, but basically we're looking at a function which increases more rapidly like this on the right hand side and decreases more rapidly on the other side. So that's 3 to the x there. But the two curves meet at this point, which is y equals 1 when x equals 0. And of course, if I change from 3 to 4 or 5, we have the same thing, the same pattern repeating. And you can also think about other similar functions like this. Suppose we considered a function like fx equals 3 to the power minus x. Well, 3 to the power minus x obviously looks exactly the same. Actually, let me use a different colour for that. Suppose we use red for 3 to the power minus x. Then that graph will have the same shape as 3 to the x, but it will simply be reversed. I hope you can see why that is, because in this case we get the same value here, let's say that was maybe minus 2, as we get here on the blue curve for plus 2. So if I just mark that equivalent point here for 2, you're obviously getting the same answer because it's just minus x in the exponent there. So from this you can deduce the general shape of all these graphs. Now, a little point worth mentioning is that we can't really sensibly draw graphs of functions like this, because when x is negative, it doesn't really, let's say it doesn't always make sense. Minus 3 to the power minus 2 minus 3 to the power minus 1/2 wouldn't make any sense. Or let's say minus 3 to the power 1/2, that's simpler, isn't it? This has no value because what you're doing there is you're trying to find the square root of minus 3, which is not a real number. Not a real number. So that's why we don't generally pay any attention to these graphs. It's not to say that one couldn't try to draw them, but it would be very complicated because some values of x have no corresponding value of the function. So for that reason, this is just ignored. We always treat this number, which we sometimes call the base. This number, I mean the number here. This number, we consider it as a positive number. Okay. So that gives you the basic idea of the graph. Most important thing, the range is always positive and it's always an increasing function. The range is all positive real numbers, let me be clear, sorry. Okay, so what is a logarithmic function? Well, a logarithmic function is just the inverse. Okay, log, let's say, base 2 of x is the inverse function of 2 to the power x. Let me just delete this little dot here. I don't know what it is. So that's a very important basic principle. So this gives you the definition of this function. Now, this number here, 2, which was previously the exponent, is now what we call the base. So we say in English log base 2 of x. So what does it mean to be an inverse function? Let's go back to the idea of that, which you already know, I hope. If y equals 2 to the x is a function, let's say equals f of x, then to find the inverse function we need to reverse the roles of x and y. Okay? So what we're saying is that the definition of the logarithm base 2 of x is the inverse function of the function y equals 2 to the x. Now, what do you know about the graphs of inverse functions? You should know that the graphs of inverse functions have a pattern with the graph of the original function. So let me try again, and maybe I'll do better this time, to draw a nice graph here. This is going to be a bit tricky. I'll draw a big line like that, make that a line, and draw another big line for my x-axis, something like that. Hopefully I can pick that up. Okay, it's not bad, I suppose. So I have my x-axis and my y-axis. So I'm going to repeat my drawing of the exponential function 2 to the x. So it should be like this, and no, sorry, I'm not really doing this very efficiently. I'll draw some kind of curve, maybe starting here. There we go, that's better, yeah. So that could be our function 2 to the power x. Now if you remember, to find the graph of the inverse function, what do you have to do? Do you remember that? Yeah, what you have to do is you have to draw the line y equals x. Now remembering that this is 1, and it's increasing very rapidly. So obviously, if I put a 1 here, this curve is above the line y equals x. So I'm now going to try to draw the line y equals x. Okay, so, whoops, to remove that. No, it doesn't want to do that. Okay, let me just try and select this one. Okay, let me just remove that for a minute. Okay, one more try. There we go. And I think I can... I'm not sure if I can change that to a dotted line. There is a way, I think. Format the line somehow. Let me just try that for a second. Hold on. Format. Oops. Something's gone wrong with my... There we go. Maybe here. No, maybe not. Okay, well, never mind. I'll investigate that later. But basically, if this is y equals x, and this is 2 to the x, then we know that the graph of log base 2x is the reflection, reflection through the line y equals x of this curve. So that reflection, if you think carefully, you'll realize it must be like this. Okay, that's not a very good example maybe, but you can see here this point has to be the point x equals 1, y equals 0, because this is the point x equals 0, y equals 1. Yeah, and you can see, but because this approaches the x-axis, so this is going to approach the y-axis. So the domain of this inverse function log base 2x is x greater than 0, because the range of the original function was y greater than 0, and the range is y is any real number. Y can be negative or positive. And it's also interesting to note that although this curve is sort of slowing down, just as this curve is speeding up, nevertheless it will achieve any positive y value. It will go up to infinity, but it will go up to infinity slowly. Excuse me, if that makes any sense. So it's really important to understand that both of these functions have this it might seem very simple, but it's a tremendously important property that both of them are monotonic increasing functions. Increasing function, again, reminder from AS Maths, means the gradient is positive everywhere, always positive. Now, monotonic is a word you might not have seen, but it means going in one direction only. Neither of these graphs have any stationary points. They never turn over and change direction. So both functions are monotonic increasing. Okay, so hopefully you should have understood so far that if this is log base 2x, we can have log with other bases, such as log base 3x or log base 10x or log base any positive number. Now it must be positive. Let me remind you, if we tried to draw a graph of minus 3 to the x, it doesn't work because minus 3 has no square root, for example. So let's just say the base can be any positive number. Positive number. So there we go. Base, this one here, this one here. Base can be any positive number, and in every case these functions are the inverse of the corresponding exponential function. Alright, now let's talk about the properties of logarithms. In order to talk about the properties of logarithms, we need to talk about the properties of the exponential functions that we already know about. What do we know about an exponential function? 2 to the x plus y is the same, and this is actually an identity, as 2 to the x, 2 to the y. This is something you should have already learned probably many years ago. And again, 2 is just an example. It can be any positive number. We know that 2 to the x minus y equals 2 to the x over 2 to the y. And we also know things like 2 to the power x y is the same as 2 to the x itself raised to the power y. So, given this knowledge, what's the corresponding knowledge for logarithms? So the most important. So what are we going to talk? What we're going to talk about here is the laws of logarithms. These things would not be obvious if you did not understand what a logarithm function is, but now you understand it's the inverse of an exponential function, so kind of the same thing must be true. So before we actually write down the laws, let's remind ourselves the key property of inverse functions is what? According to certain restrictions, this is always going to be true. I won't get into that now, what those restrictions are, but basically it's required that the function itself be invertible. Yeah. Now, are these functions invertible? Let's go back and look at this graph here. Look at this graph here. Is this an invertible function? Yes, it's invertible. Function invertible. So in other words, what I'm trying to say is that this rule can be applied because the function is invertible, and the reason it's invertible is because it's one-to-one. Yeah. So one-to-one functions can be inverted. Functions are one-to-one if 1y corresponds to 1x and 1x corresponds to 1y, and that is true here. So we can apply this kind of rule. Now, what does this rule here say in terms of exponential and logarithmic functions? Let's take the example of, again, in this case we'll use log base 5x. What's the inverse of this function? The inverse of this function is the corresponding exponential function 5 to the power x. So if we apply this rule here, we're going to get the following statement. 5 to the power of log base 5x is equal to x. Yeah? Assuming, of course, that x has a logarithm, remembering that the logarithm function is only defined for positive values of x. Again, let's look back at the graph. Here's logarithm. Actually, this is log base 2x, but it doesn't make any difference. We can only put in positive numbers. The domain is positive numbers. So here I should put in brackets if x greater than 0. So if x is greater than 0, we can calculate log base 5x. Then if we apply the inverse function 5 to the x, we're going to get x. Okay? So we can apply this idea to what we already know about exponents to get the laws of logarithms. So let's start with the addition law. I think it's called that, but I mean, who cares what they're called? We just need to know what they are, right? Let's write, for example, log base 5a plus log base 5b. Now, if we apply the inverse function 5 to the power x, we get the following. So let's say equals what? Yeah. Well, 5 to this whole left-hand side is log base 5a plus log base 5b. That must be equal, because of the way exponents work, to 5 log base 5a plus times times 5 log base 5b. Now these are inverse functions, so this is giving me a times b. Okay, so given that that is true, let's see that as one equation. 5 to the power log base 5a plus log base 5b is equal to a times b. Now let's apply the inverse function again on the whole thing. Log base 5 brackets the left hand side, 5 to the power log base 5a plus log base 5b must be equal to log base 5ab. Yeah? So again, because the functions are one-to-one, because the functions are monotonic increasing, 1x corresponds to 1y, 1y corresponds to 1x. So it might be worth making a note here that this is always going to be true. Yeah? If we have the same x value, we always have the same y value, assuming the function is defined at all. Yeah. For example, here I could not put a and b as I could not put a and b as negative numbers. I can't use a negative number for a logarithm. You know, I can for an exponential function. And more importantly, it works the other way, doesn't it? If fa equals fb, that means if the y values are the same, then the x values must also be the same, because there is no turning point, there is no maximum or minimum, so we can't get this case. Let me be really clear, maybe you don't understand what I'm saying. In this case, we have a function here. This function value could correspond to two x values, you see. That's x1 and maybe x2 here. So this kind of thing is not going to happen if the function is monotonic increasing. So I hope you followed that. In a way, it's a little bit obvious, but it's also maybe not obvious. So anyway, we got this far. We've decided that log base 5 of this stuff must be the same as log base 5 of this stuff. And now we can apply the maybe let's put a little bracket there so it's really clear. Now we can see that log base 5 of 5 to the something is the original thing back. So log base 5a plus log base 5b equals log base 5ab. So that's the sort of the first and the main rule of logarithms. Now how does it work? So that's the one you're going to use most commonly. Now how does this work with subtraction? What about subtraction? Well, it's basically exactly the same, right? Log base 5a minus log base 5b. So imagine we're subtracting two logarithms with the same base. We're going to get log base 5 a over b. Now why a over b? Is it obvious or not? You can also well, there's another way to understand it without obviously I could go through this proof process again, but it should be fairly obvious. But there is another way to understand it, which I'll show you in a minute. Okay, so let me just pause a moment. Okay, so the other logarithm law is a consequence of this first one. So if I could try and be especially clear, this first one, the law which allows you to calculate the logarithm of how to change two logarithms into one if you have an addition. Yeah, but the other one is sometimes called the power law. Is really a consequence of that. So because, for example, suppose I had log base 5 of a times a, which could also be written log base 5 of a squared. Well, according to this first law, you can see that's the same as log base 5a plus log base 5a, which could also be written 2 log base 5a. And by the same logic, we could change to log base 5 of a to the power 6, and we would see that by this same process of logic we get 6 log base 5a. So this leads us to the third of the laws, which would say that log base, and I'm sticking with the base 5 here, you can change the base to anything, log base 5 of some number a raised to a power n will be, so using brackets there, all of that is being put into the logarithm, will always be the same as n times log base 5 of a. So that's the other law. Now this number n in my example here was a positive integer, but actually it can also be a fraction, and the same rule works. Okay, so to summarize, the laws of logarithms can be found in the book, so do look in the book and read the general form of the law of logarithms, but they're very powerful calculation tools. They allow you to change, to be really clear, change a sum into a product. You see how a sum here, a sum of two logarithms, is being changed into a single logarithm of the product, and here a difference of two logarithms is being changed into a quotient, a division, again inside the logarithm. So you'll see these rules being used again and again in exam questions and other situations. And the last one here is a natural consequence, is if you have a power, you can take the power outside. Maybe actually to make this stuff a bit clearer, I'll give you some concrete numerical examples of how this works. Suppose we take the logarithm base 10 of 100. What is this? Okay. Remember, the logarithm base 10 function is the inverse of the function 10 to the x. So what you're really doing in this, if you're trying to figure out what the answer is you're trying to say, what's x? What number x do I need to make 100 from a base of 10. So what power do I need of 10 to make 100? Obviously the answer is 2. Yeah? So the answer is 2. And how would this connect with the law of logarithms? Well, one way to think of it is to say that what we're looking at is log base 10 of 10 squared, because 100 is 10 squared. Well, according to the power rule we just looked at, we see n here. If there is a power n, it can be taken outside and become a multiple. So that's just equal to 2 times log base 10 of 10. Now what's log base 10 of 10? Well, that's the number we need to raise the number 10 to the power to get the answer 10. So the answer is 1. So it's 2 times 1, which is 2. And you can look at lots of simple examples like this to help you understand logarithms better. For example, how could we simplify maybe this? Find a good example. Log base 327. You should recognize that that's equal to log base 3 of 3 to the power 3. So that's equal obviously to 3. Obviously the main law of logarithms here allows us to simplify or to recognize patterns in logarithms. Maybe I could give an example like log base 4 18 plus log base 4 what would be a good example? 2. So suppose that x is equal to this. How can we simplify this? Well, the answer is because we have the sum of two logarithms, we can use this principle to change it into a single logarithm, which is log base 4 of 18 times 2, or log base 4 of 36. And if we wanted to, we could change it in another way, because we could recognize that this number 36, log base 4 36, would be log base 4 9 times 4, which again, going backwards and using the identity in the other direction, I can split this into two logarithms, log base 4 of 9 plus log base 4 of 4. So I want you to recognize that we may find in different situations that using the equation in different ways helps us. So here you could say this is a better way to write the answer. Log base 4 9 plus log base 4 4. Now what's log base 4 4? Well, that's just 1. So we could write this 1 there. So depending on the problem, you might want to change the logarithms into different forms. And obviously getting a lot of practice with that is a very helpful thing, so do use the exercises in the book to help you there. Alright, so this is the basic idea of the laws of logarithms. You can certainly go further with that, but it should get you started at least. So let's have a quick review where we're up to. Basically we know that the properties, especially about the graphs, I hope, the domain and range, the increasing function and the inverse function features of these functions. They're very important. Laws of logarithms I've just covered very briefly. Now let's quickly mention special bases and go on to the number e before we get into the real, the real task, which is to know how to answer the exam questions. So yes, special bases. There's only two special bases really. And one of them really is only special because of history. So 10 and e. So if we use a base 10, logarithm base 10x, it's sometimes written as lgx. Notice there's no o here. Now why is this special or important? It's special or important for the same reason that we have such a thing as standard form. You're probably all familiar with writing numbers like this. Yeah? If you're doing science, it's very useful to think about powers of 10. It's a nice standard way of doing things. And historically, logarithms base 10 were used to do calculations. Now you might wonder why such a complicated thing like a logarithm, how is that useful for calculations? Well, it's useful because, as we saw in the main law of logarithms here, yeah, a sum of logarithms is equal to a logarithm of a product, and that means that you can change a multiplication problem into an addition problem. Yeah? If you're multiplying two huge numbers like 3789.12 times 156, 1567, this kind of multiplication is very tedious to do by hand, very difficult, slow, boring. Of course, nowadays we have calculators, so we don't worry about this. But when there weren't calculators, yeah, without calculators, it was very useful to change a multiplication problem into an addition problem, because addition can be done pretty quickly even if you don't have a calculator. So what people used to have was tables telling them the logarithms of all different numbers, and use those logarithms, add the logarithms together to get the product. So I won't go into any detail about that because it's only history, it's not important anymore. But it does at least give you some clue as to why we even talk about logarithm base 10. So sometimes on the exam you're going to see something like this, LG, LG7 plus LG10 or whatever. That's why it's there, it's logarithm base 10. So I'll say no more about that. However, the other base, the other special base, sometimes called the base of natural logarithms, is e, is the number e. So e, as I said to you before, is approximately 2.71828, although it's very easy to remember a lot more digits. Okay. It's a little bit more than you get on the calculator there, but of course it has its sort of sister number in mathematics, pi. And why is it like pi? Only because it's and so on. Only because it's a transcendental number. That's quite difficult to explain what that means, but it's an irrational number. It doesn't have any expression like, let's say, not equal to p over q, yeah, where p and q are integers. There are no integers we can use to make a formula for e, so it's decimal expansion. This is its decimal expansion, continues forever with no repeating pattern. No repeating pattern. So this is quite a mysterious number. It's nothing like what am I trying to say? It's not like pi in that pi has a very easy definition. Pi is just the ratio of the circumference to the diameter of a perfect circle. So that was discovered many thousands of years ago, but E was not really understood at all until about maybe 400 years ago. I don't remember exactly, but the point is it has this very subtle, not at all obvious meaning. So I want to say, before I say any more about E, let me just point out that logarithms can be taken to base E, so x or something, and this function is written lnx. ln means natural logarithm, although it's ln not nl, but it means natural logarithm. And so we're using this word natural because there's something very special about taking a logarithm to this specific base. Hopefully you'll understand this a bit better when we talk about calculus, about differentiation and integration in this course. But for now I do want to give you a little bit of a flavour of why E is important. So I'm just going to pause the video here and show you some information about that. Okay, so I'm back here, and what I'm showing you now is just a couple of slides that I like to show to my students about E. First of all, there is the number. Obviously it looks a bit ridiculous. You can see the first few digits that I already showed you. But it goes on forever. It has no repeating pattern, just like pi. And its traditional name is the base of natural logarithms, but I don't think that name is actually very helpful. It doesn't help people understand it really. I'd prefer to call it something like the natural rate of continuous growth or something like that. But anyway, that's its official title, and it's always written as a lowercase e. Now, I want to give you an example that will help you see why E comes about naturally. There's nothing artificial. We didn't just choose this number for no reason, okay? But you have to do some calculations to see where the number comes from. So here, I'll give you an example. Imagine you have $10,000 in a bank account. You're going to get 10% interest every year. So, simple example, maybe you have you have $10,000 in the bank. Simple way to understand it is 10% of 10,000 is $100. So you would imagine at the end of the year you have $10,100. But you may or may not know that banks don't always work like that. It depends on the case. You see, if it's possible to recalculate the amount of money in the bank at different periods of time. You can recalculate every year, sure, but you could recalculate every 6 months, or you could recalculate every month. So have a think about this question. You suppose you had 3 choices. You get 1 interest payment every year, 10%, or instead you get 2 interest payments of 5%. So for example, maybe 1 in June and 1 in December. Now that still adds up to 10%, but does it add up to the same amount of money? Think about that. Or we could have 12 interest payments of 5/6%, so 1 every month, still adding up to 10 after 12 months. But again, is it really the same? So do have a think about it and pause the video if you haven't thought about it before. So which do you prefer? Well, almost everyone, if they think about it, is going to prefer the last of those 3 choices. 12 interest payments of 5/6% every month will give you this much money. So we will get an exponent or a power of 12 here, because we're getting, this is 10% divided by 12 plus 1 raised to the power 12, instead of just 1 plus 0.1 or 1 plus 0.1 over 2 squared. Of these 3 numbers you can easily verify with a calculator. This one is the largest, although it must be said that the difference is very small. In any case, it's small. Okay, but the main point is that if you calculate interest more frequently, you get more money at the end of the year. So this is an effect of what's called compound interest, and what's happening is that in this case you're getting interest on interest. Okay, so if you study accounting or business or something, you almost certainly know about this already. But let's think about the real logical conclusion of this. Suppose we change it not to every month, but every single day. Then we get a crazy number like this. 1 plus 0.1, that's 10%, divided by 365, the number of days in the year, and raised to a power of 365, again the number of days in the year. Now the amount we get is more than $11,000. Oh, sorry, 10%, did I say? Okay, of course 10% is $1,000, not 100. So we get actually $51.56 more than we would if we got a single interest payment at the end of the year. So it's a small difference, but it's not zero. And after all, you know, this is mathematics. We're not only interested in the practical reality, we're interested in the fundamental truths. This is better. Yeah? The more frequently we calculate the interest, the more interest on interest we get, and the more growth we get in the money. If we change it to every second, it gets even more ridiculous, right? So this number is just ridiculously large. This is the number of seconds in a year. And now again we see that the money has gone up. It's only gone up by about 15 cents, but it's gone up. So I hope you can see where I'm going with this. If I change this to once every 10th of a second, once every 100th of a second, effectively I can keep going on like this forever. But what we start to notice is that the number is getting closer and closer to a single value. And as it turns out, if you do a little bit of jiggery-pokery with the numbers, you'll see that what you're really multiplying this 10,000 by is a certain number raised to the power 0.1. That number is 2.71828, and it gets closer and closer to a single number as the compound interest frequency gets larger and larger. That is the number E. And that is actually the definition of the number E. It's the number that you would need to put in the brackets here in order to get the correct amount of money at the end of the year if the interest was recalculated infinitely often. So it seems a bit strange, but you can see now, I hope, why I think of E as like a kind of natural rate of growth. So I'll leave this to one side for now, and I'll go back to our original... Sorry, slight delay there. I'll go back to our original discussion. So now I hope you have some idea what E is. As I said at the beginning of this presentation, you don't really need to know anything specific for the exam. But you do need to know that lnx is called a natural logarithm, and it's the base E. And this, of course, is on everyone's calculator. Okay, let's now look at a couple of examples of exam questions to see how these ideas are used in practice. So I'm switching over here to another note file. First of all, what does it say in the syllabus? It says you should know simple properties and graphs of the logarithmic and exponential functions, including lnx or logx. Well, I say logx, but it's lnx or natural logx and e to the x. Series expansions are not required, so if you don't know what that means, it doesn't matter. You need to know and use the laws of logarithms, including the change of base of logarithms. I forgot that. Let me go back a moment and show you the change of base and of logarithms. Okay, change of base of logarithms. I think the best way to understand this, because it's a bit confusing if you haven't seen it before, is probably to consider a very concrete example. Suppose I wrote the exponential equation 8 to the power x equals 64. Now, I'm sure it doesn't take you long to figure out what x should be, but that's not the point of this exercise. Now, suppose I prefer dealing with base 2 instead of base 8. So here 8 is acting like the base, yeah, but I prefer base 2. So to deal with that, to as it were solve this equation, I'm going to write log base 2 of the left hand side equals log base 2 of the right hand side. As we already discussed, we can always do this because the function is one-to-one. That's a critical point. So we can take the left hand side and the right hand side and take the logarithm of any base and apply it to both. It will still be true. Now I want to apply the laws of logarithms, and I can see here that I have a power inside the logarithm. So if I go back to my laws of logarithms here, when I had a power inside the logarithm, I could take it outside as a multiple. So that's what I'm going to do here. I'm going to write, therefore, x times log base 2 of 8 equals log base 2 of 64. Now that follows that x is equal to the ratio log base 2 64 over log base 2 8. Now, by the way, this should be obviously true to you because 64 is the sixth power of 2, 2 to the 6, so this is 6, and 8 is the third power of 2, 2 to the 3, this is 3. The answer is 2, and you can verify, yes, 2 is the correct answer. So why did I show you that? Because if you look carefully at this equation here, what is it really saying? It's saying that if I want to find the number to which I must raise 8 to get 64, I can do so by dividing the ratio of two logarithms of the same base. Notice they have the same base here, 2. What's maybe not immediately obvious is this number could have been anything. Yeah, I chose base 2, but I could have chosen base 3. Then I would have 3 here, 3 here, 3 here, 3 here, but it would still be true. Okay, so we can see, and you can verify this by a couple more examples if you like, that in general we can write, let's say, log base, how shall I do this, log base C of A is always equal to log base B of A over log base B of C. Yeah? So this is the change of base of logarithms. So we can always change the base using this formula. Again, it's in the book, but do try to remember it, because I have a feeling it's maybe not on the formula sheet. And it comes directly from this power law of logarithms. Notice the x here, the x came outside the logarithm and became a multiple there. So that's how we change the base of logarithms. Right, let me go back to the other window with the syllabus here. So we know how to use the laws of logarithms, including change of base, and we can solve equations of the form a to the x equals b. I hope we can do that. Perhaps I should make that a little clearer. Let's give a completely random example. Suppose I have the equation 7 to the x equals 65. How would I solve this equation? Have a think about it. Pause the video. Okay, so of course what we can do here is again apply the law of logarithms. We can either just directly observe that x is equal to log base 7, 65, or, and I emphasize this is an important idea, we can choose a different base. If we prefer to use log base e of or ln, we can solve it like this. ln of 7 to the x equals ln 65. Now, why might we want to do this? Because the calculator has the ln button. Yeah. Oops, interesting brackets there. The calculator has the ln button, which is the natural logarithm. Now we apply the power law of logarithms. X times ln 7 equals ln 65, and obviously that means x is ln 65 over ln 7. Okay, so you can calculate that on the calculator and that one, so you get the answer and you can write it out. Notice what I've done here is exactly the same as what I just did here, because I've just changed the base to e. Okay, so I hope so far it all makes sense. Let's look at a couple of examples here. Let's look at this one. This is from some past paper, I forget which one. So part 1, given that log base 9x equals a log base 3x, find a. So what should we do here? Well, we could we could apply the change of base formula. Let me use a black pen here. Log base 9x, well, that's equal to log base 3x divided by log base 3 of 9. Now log base 3 of 9, you should recognize 9 is 3 squared, so log base 3 of 9 is 2. So that's a half log base 3 of x. So the answer is a is equal to 1/2. And for part 2, obviously a similar idea, log base 27 of y is b log base 3 of y, or you could almost do it without calculating, couldn't you? But let's just write it out. Log base 27 of y equals log base 3 of y over log base 3 of 27. So it's 1/3, because 27 is 3 cubed, log base 3 of y. So b is 1/3. And the final part of the question, let me just move this out of the way. How do I do this? How easy is this? Perhaps I can select it or something. Yes. I'll move this downwards. There we go. There we go. Right. So the third part of the question was solve for x and y. So back to the pen. Solve. Here we are. Solve for x and y, the simultaneous equations, blah blah blah. And you can see they've already set this up for us. What they're telling us is they're saying, look, these are simultaneous equations, fine, but we have different bases, 3, 9, 27, 9, and so on. I wonder if I can erase that. Let me just try to erase my scribblings there. There we go. So we have 3 and 9, and 27 and 9. We have 3 different bases, but as will often be the case, they're quite closely similar bases. They have some relationship. So we deduced here that we can replace all the bases with base 3, just as we did in parts 1 and 2. We changed the base to 3, changed the base to 3. So let's rewrite the 2 simultaneous equations all in base 3. I have, where shall I write this? Here, I suppose. I have 6 log base 9x, which is 6 over 2, so that's 3 log base 3x. That's that one there, plus 3 log base 27y, that's 3 times 1/3 log base 3y, so it's plus log base 3y equals 8. That's my first equation, and my second equation is log base 3x. Now log base 9y is 1/2 log base 3y, so I've got plus log base 3y equals to 2. That's my second equation. Now we have a very trivial system of equations, so I'm just going to subtract 1 minus 2 gives me 2 log base 3x equals 6. Therefore log base 3x equals 3. Therefore x is equal to 1, because well, I hope that's obvious, and therefore I can deduce that log base 3y is equal to 2 minus log base 3x, which was 3. Sorry, hold on, I'm just double checking something. I've got a slight brain freeze here. Log base 3x is I'm sorry, I made a ridiculous statement just there, didn't I? Just in case anyone else has the same kind of problems I do, you can do this really carefully. Excuse me. You can see this is an easy way to deduce the sorry, that was a 3. So x is 27. Now this is 2 minus log base 3, so that's minus 1. So now we're asking the question, if we raise to the power 3, y is 1 over 3. So our answers are x is 27, y is 1 over 3. Okay, let's look at another example. These ones are fairly kind of straightforward examples. I'll need to maybe insert another page if I can do that. Insert page, yeah, maybe there. Okay, yeah, I know what to do. Good. Let me move all this stuff out the way. Yeah, that makes a lot more sense, doesn't it? And then I can maybe move this one a bit higher up. Okay. Yeah, let's move this one up here. Okay. So this will be our second example. These should be pretty easy marks on the exam for most people, because you just have to be a bit careful, that's all. Alright, let's look at the first part of this question here. Sorry, let's get the colour right. Okay, so in part 1 we have very simple manipulation of exponents. So let's look at the left hand side. I've got 2 to the power 2, that's 4 to the power x, divided by 2 to the power 5 minus x. Okay, now because that's a division, that means I've got 2 to the power 2x minus brackets 5 minus x. So let's simplify that down. That's equal to 2 to the power 3x minus 5. I hope that's right. And the right hand side, using a similar kind of approach, you see what I'm doing here is I'm trying to get my exponents to be all the same. So here 4 is like 2, so I'll just make it 2 to the 2, here 2 to the 4, here 8 is 2 to the 3, so we can do everything with 2. That's probably the best way to do it. Not the only way, but okay. 2 to the power 4x divided by, now 8 is 2 to the power 3, and that's being raised to a power x minus 3. So we can see we're just multiplying exponents here. 2 to the power 4x minus, because this is in the denominator, minus 3x plus 9. So this is minus 9, but it's in the denominator, so plus 9. So it's 2 to the x plus 9. So now we have this equation. The left hand side is equal to the right hand side, so I've got 2 to the power 3x minus 5 is equal to 2 to the power x plus 9. Now you might wonder for a moment whether it's valid to just assume that 3x minus 5 must be equal to x plus 9. Well, it is. If you were paying attention, you know that these functions are monotonic. They're one-to-one. And so if you want to be really exact, you can proceed as follows: log base 2 of 2 to the 3x minus 5 equals log base 2 of 2 to the x plus 9. And log base 2 of 2 to the something is that thing itself. 3x minus 5 is equal to x plus 9. And therefore we get 2x equals 14, so x is 7. So the solution is x is 7, and there's only one solution. Okay. Obviously don't always assume that there's only one solution. Sometimes it's not true, but here it is. Okay, that was the first part. I think I got that right. And the second part. The second part is I'll just copy it out so I don't lose it. LG 2y plus 10 plus LG y equal to 2. So we need to solve this equation. Well, you should immediately notice a couple of things. First, LG is log base 10. Okay, so it's base 10. And the second thing you should notice is that we have on the left hand side a sum of logarithms, so we can convert it to a product. So the logarithm base 10 of 2y plus 10 multiplied by y is equal to 2. Now if I'm trying to solve this equation, I need to get rid of the logarithm, so I'm going to use the inverse function. 10 to the power of LG y 2y plus 10 equals 10 to the power 2. Well, that's just 100. So this cancels the logarithm and I get 2y squared plus 10y equals 100, and therefore I have, now we can cancel the 2 here, can't we? Y squared plus 5y minus 50 is equal to 0, and now I need to factorize this quadratic. So how do I get 10 times 5? Yeah, so I need to do plus 10 minus 5, right? Y plus 10, y minus 5 equals 0. Now here I want to say be careful. The more you start to get involved with exponential and logarithm functions, you're going to understand you need to be careful whether your solutions are valid. If you just write y equals 5 and y equals minus 10 without checking, that's wrong. Look back at the original equation. Consider the possible solution y equals minus 10. Is it a valid solution? The answer is no, because if y were minus 10, then log minus 10 would not be defined. Yeah? Logarithms have to have positive input, positive, the domain is positive numbers. So that's no good, we can't have that. And it would also be true here, because 2 times minus 10 plus 10 would also be negative. So on the other hand, if y is plus 5, that's no problem. Let's give me a positive number here, and you could actually double check. If y is plus 5, you've got log 10 plus 10, log 20, plus log 5, and log 20 plus log 5 is equal to log 100, which is indeed 2. So the correct answer is that there is only one answer, and that answer is y equals 5. Okay, I'm going to stop this video here. There will be a second, much shorter video, just covering a couple more details about this topic. To be specific, the second video will cover whoops, sorry about that. The second video will cover the linear law problems. Okay, and we've actually partly done the exam questions as well. Alright, so see you next time. Thank you.